Sir Fred hated this model, and so he nicknamed it the Big Bang because he thought it lacked elegance. But the nickname has stuck ever since. And it says that 13.8 billion years ago, the whole universe, everything that I've shown you, the whole lot, was small enough to fit through the eye of a needle. At that point, it begins to expand rapidly in what's nicknamed the Big Bang. Don't think about it as an explosion. Think about it as a rapid expansion. We'll come back to that. In the next slide, my sisters and brothers, forgive me, because I've attempted to put the whole history of the universe on one PowerPoint slide. This is a little optimistic, to say the least. Here we are, our present age is 13.8 billion years. Some of us feel it more than others at times. And poor old Mike, having talked all day, probably feels 13.8 billion years old. And currently, our current models of physics allow us to say, for most of us, that we've got good confidence in understanding what the universe was like when we go back in time. So we think we know what the universe was like when it was only 1 million years old. That's a big jump, by the way, and for those of you who are mathematicians, this is not to scale. We think we know that what the universe was like through our current models of physics when it was only 1 second old. And if that isn't sufficient, a number of us think that our current models of physics describe the universe pretty well back to 10 to the minus 43 of a second. Now that's a shorthand way of writing 1 divided by 10 followed by 42 zeroths of a second. Now, if you're not a mathematician, if you're a biologist or an engineer or a normal person, if you know what I mean by that, you'll probably say, isn't that 0? Such a small fraction. Not quite. At that point, our current laws of physics break down. And you can imagine it is very frustrating to physicists. Because you've been able to describe the universe from 13.8 billion years right back to 10 to the minus 43 of a second. And then you can't get right back to 0. It's rather like you've been watching on the television a murder mystery or a very exciting sports match, a cricket match. And just before the final over, or just before in the thriller the murderer is revealed, your television breaks down. You've watched the whole thing, and then you can't see the really interesting bit. We'll come back to that. 10 to the minus 43 of a second, the universe is very small, fraction of a centimetre across. As it begins to expand, it cools. 10 to the minus 35 of a second, quarks appear in the universe. Between 1 second and 1,000 seconds of the visible matter, about 75% is hydrogen, 25% is helium. And then to cut a very long story short, over billions of years, these great clouds of hydrogen form stars and galaxies. And to be honest, we don't understand entirely all of the intricacies of that. But this is a broad outline. And some of you will say, well, as the Lord said to Job in the Old Testament, where were you when I laid the foundations of the world? You could say the same thing to cosmologists. Where were you? Now, do you remember when Mike talked about the Big Bang as singular? You can't ask an undergraduate to go into a lab and explode a universe in a Big Bang. It's a one-off. And so here science is not about our normal experience of doing science, of repeatability of experiments. Science here is a bit more like history, where you look for clues or pieces of evidence with which you reconstruct the best model of what you think happened. And 3 pieces of evidence, particularly in the 20th century, were important for believing the model of the Big Bang is the best interpretation. The first occurred from about 1910 through to 1930, and it was called the redshift of galaxies. And astronomers looked at galaxies far away from us, and the light from those galaxies was redder than they thought it should be. And in a classic paper in 1929, Edwin Hubble said, "That's due to redshift," he said. Now, you all know what redshift is, don't you? I mean, theologians, of course, well, maybe you don't, but we know what redshift is if we put it like this. Redshift is a form of the Doppler effect. And the Doppler effect is that the wavelength is dependent on whether something is moving towards you or away from you. So if you stand by a road and a car comes towards you and away from you, the sound is different that you hear. And it goes, meow. That sounds more like a cat than a car, forgive me. Imagine a high-speed cat coming towards you or away from you. The sound that you hear is different depending on the motion towards you or away from you. Now, same thing with light. Imagine this cat, high-speed cat, is holding a torch and is moving close to the speed of light. As the cat comes towards you, the torch will appear blue. As the cat moves away from you, the torch will appear red. And what the astronomers had interpreted through their observations was that when we look at galaxies around us, all the galaxies are moving away from us. A little more complicated than we understand now, but basically it was a good interpretation. And if everything was moving away, at one point it was all together. First piece of evidence for the Big Bang. Second piece of evidence for the Big Bang happened in 1965, and some folk were trying to do early communication experiments by bouncing microwaves off satellites. The trouble was that they kept getting an interference on their experiment. And they tried everything to get rid of it. They even thought at one point it was bird droppings within their antennae of the telescope. They cleaned out the antennae. It's a hard life being an astronomer at times. What they discovered was not bird droppings, but a form of radiation left over from the Big Bang itself, the microwave background radiation. And the third piece of evidence was the amount of helium in the universe, which we were able to measure in the late 1980s and turned out to be in a good agreement with the theory of the Big Bang. And as we've looked at this model over the years, and let me again just re-stress what Mike has said. When we talk about science at this scale, we never talk about proof, okay? We never talk about the Big Bang is proved. That's not language that cosmologists use. We talk about how this model has evidence for it, how it has evidence which questions it, but ultimately you weigh the evidence and say this is a reasonable explanation of the evidence. And as we've looked at the microwave background, what we've discovered is that lots of things about the Big Bang seem to be good, but there are some big questions that we don't know the answer to. I mean, really, really big questions. Let me share some of you. The first is that there is a form of the universe in dark matter. This is matter, unlike stars, that we know is there because of the force of gravity, but it doesn't shine in a way that we can see it. And the embarrassing thing for astronomers like me is that about 26% of the universe is in dark matter. And we call it at the moment dark matter because we don't know what it is. So 26% of the universe, we don't know what it is. Now, if that's embarrassing, even more embarrassing is that another 69% of the universe is in something called dark energy. And we call it that because we don't know what it is. That means that at the moment I stand before you only knowing what 5% of the universe is made of. Again, you might say to yourself, he's come a long way from England to say that he only knows what 5% of the universe is made of. But at least we know that we only know what 5% of the universe is made of. We're still working on the other 95%. Now that's a reminder to me of something about the humility again, which Mike talked about. Even with something like the Big Bang, there are many questions that we don't understand. The third question with the Big Bang is back to that thing. Do you remember I said 10 to the minus 43 of a second, our laws of physics break down? And that's because of the limits of our two great theories of 20th century physics, quantum theory and general relativity. Which means that at 10 to the minus 43 of a second, we at the moment have a question mark. The reason for that, well, I haven't got time to do quantum theory and general relativity in detail this evening. And even tomorrow, when I talk about them a bit more, I won't do them in great detail, but we will talk about them. But let's just, for a moment, work out why these things happen at 10 to the minus 43 of a second. General relativity, Albert Einstein, describes the universe on the very largest of scales. Okay? It describes galaxies and the universe itself. And everywhere you apply it, it works beautifully. And the people who work on relativity, let's say, are the front row here. They are distinguished general relativists. And everywhere they apply general relativity, you do it beautifully and it works. Down the other end of the corridor in the physics department, another group of physicists, they're equally brilliant. They're quantum physicists, quantum theorists, a bit like Planck. And they describe the universe on the very smallest of scales. And everywhere that you apply quantum physics, it works beautifully. Now, most of the time, you guys never meet. You get on with your work, you're on the large scale, you're on the small scale.